need to teach the law of conservation of energy in a way that will blow people's minds.
Yeah guys, this needs to be epic.
Let's do an intense battle scene! But we actually need some content.
I'm sure.
So class, what is energy?
Something that this class just doesn't have.
Incorrect.
As always, Ben fails to understand even the simplest of concepts. Energy is actually the capacity of a physical system to do work and is measured in joules, which has the symbol J, capital J. 1 joule is equal to 1 kilogram meter squared over second squared.
Stellar job, Clement. Simmer down, Ben. Now on to the rest of my lesson. So the law of conservation of energy states that energy can neither be created nor destroyed. There are many different types of energy, but we are going to focus on 2, kinetic and potential energy. So kinetic energy is the energy of motion. So an object moving faster has higher kinetic energy than one at rest. So the equation for kinetic energy is EK equals 1/2 mv squared. So EK represents the kinetic energy, M represents the mass in kilograms, and V represents the velocity in meters per second.
I'm literally gonna fall asleep.
Yeah man, this is so boring.
Did anyone ask for your opinion? As I was saying, potential energy is gravitational or positional energy. So an object further away from the Earth will have higher potential energy than an object that is close to the Earth. The object further away has higher potential energy because it has the potential to do more work if it falls. So the equation to find potential energy is Eg equals mgh. So in this case, Eg is the potential energy, m again is mass measured in kilograms, g is the acceleration due to gravity, and on Earth this is 9.8 meters per second squared, and h is equal to the height in meters. Now the amounts of each type of energy can change, but they always add up to the same total amount of energy, or mechanical energy as I call it, and it is called in the world of physics, due to the law of conservation of energy. So the equation for total mechanical energy is E equals Eg plus Ek. Okay class, now we're going to head over to the computer lab.
And make sure to turn off the lights when you leave to conserve energy, guys.
Joke's on you, energy is always conserved.
But seriously, turn off the lights, guys. You know, we could all save so much energy if we just turned off the lights.
Okay, Cricket, nobody cares. You disgust me.
Okay, guys, this movie sucks. Time to spice it up.
By the way, Cricket, do you have that pen I lent you?
You mean this one? I do, but you're not gonna get it because you insulted all of my eco-friendly boobies, and you're gonna die!
is gonna be spectacular.
Cross the line. Prepare for battle. I think I throw the ball side.
Oh wait, okay.
If Ben misses the person he's trying to hit, which happens quite often, the ball will hit the ground. Let's figure out its energy right before it hits the ground. Since it is very close to the ground, it has no potential energy, it only has kinetic energy. Therefore, its mechanical energy can be calculated using the equation Ek equals 1/2 mv squared. Since we already know the mechanical energy, 2.72 joules, let's solve for its final velocity. So we have 2.72 equals 1/2 times 0.1 times v squared. If you multiply 1/2 times 0.1, you get 2.72 equals 0.05 v squared. Now if you divide both sides by 0.05, you get 54.4 equals v squared. If you root both sides, you get 7.38 equals v. So the final velocity is 7.38 meters per second. Wow!
You may have won the battle, but the war has just begun. You'll see me in your worst nightmares.
So kids, this is how it works. Remember how at the beginning of the video we talked about the law of conservation of energy, which states that energy always stays the same? Well, we're going to show you how that works using another example. Right before he let go of the ball only had gravitational energy. This is because it was motionless, so its kinetic energy was equal to 0. However, since it was above the ground, it had potential energy. Again, he was holding it 1 meter above the ground, so its potential energy was 0.980 joules.
Now let's find the energy of the ball at the middle of the drop, 0.5 meters above ground. At this point, the ball has both kinetic and potential energy. We can find the velocity of the ball to put into the kinetic energy equation using one of the 5 kinematics equations relating to velocity, acceleration, and distance. v2 squared equals v1 squared plus 2ad, but we will not be covering this equation today. Just know that v2 represents the final velocity, v1 represents the initial velocity, a represents the acceleration, and d represents the displacements of the ball. This ball has a velocity of 3.13 meters per second at this point. Now we must calculate the total energy by using the equation E equals Eg plus Ek. The total energy is equal to 0.98 joules again. Coincidence? I think not.
Finally, let's calculate the energy of the ball at the end of the drop. At this point, the ball has no gravitational energy because it is almost on the ground. It only has kinetic energy, so we must plug our information into the equation EK equals 1/2 mv squared. Again, we can find the velocity of the ball at the end of the drop using the equation v2 squared equals v1 squared plus 2ad. So v1 equals 0 because Ben is just holding the ball and it is not moving, so it has no velocity. Acceleration, as always on Earth, is 9.8 meters per second squared, and the distance that the ball falls is 1 meter. So you have v2 squared equals 0 squared plus 2 times 9.8 times 1. Once you solve all that, you get v2 squared equals 19.6. And if you root both sides, you get v2 equals 4.43. So the ball has a velocity of 4.43 meters per second right before it hits the ground. Now we can use this velocity in the equation EK equals 1/2 mv squared to find the kinetic energy. As you can see, at all points in the drop, the energy is the same, proving the law of conservation of energy.
To show this to our fellow classmates and scholars.
Whew, that was super informative and entertaining.
Our job here is done.